Hello everyone, welcome to the final session of problem solving for analog communication in NPTEL course E135. So, based on the 12 assignments that have been given in the 12 weeks of the course, we have conducted 12 problem solving sessions. Now, this session is an extra session in which we aim to address your doubts, if any. But since none of you seem to have joined in the meeting, then I will, of course, solve some extra questions and you can see the recording. And you can revert back to in the discussion forum or to us at any time with any doubts, and we will be happy to entertain them. So for now, we will be discussing some extra questions, namely questions that have appeared in the GATE examination conducted by IITs. So a lot of you might be aiming to give the GATE examination. So in GATE examination, the following communication questions have been asked, and we will attempt to solve some of them in this small session of 1 hour. So let's begin. Okay. Uh, Okay, so let's start with the first problem here. A given phase modulated signal, sorry, let's share the screen also in case anyone joins. So the first question is question number 3. A given phase modulated signal has a maximum frequency deviation of 50 Hz for an input sinusoidals of unit amplitude and frequency 120 Hz. The required frequency so a given phase modulated signal has a phased frequency maximum frequency deviation delta f of 50 Hz for an input sinusoidal signal of unit amplitude and frequency 120 Hz. The required frequency multiplication factor n to produce a maximum frequency deviation of 20 kHz when the input sinusoid has a unit amplitude and a frequency of 240 Hz is. So, in question number 3, there are two cases given. The first case is case 1. Case 1. In this, the input frequency f is given to be 120 Hz and the frequency deviation due to phase modulation is given to be delta f equal to delta f is equal to 50 Hz. So delta f is 50 Hz. Now, in case 2, the f is given to be 240 Hz and delta f is given to be 20 kilohertz. Now, for the first case, the modulation index beta 1 is equal to delta f by f is equal to 50 by 120. And in the second case, the modulation index beta 2 is 20 kilohertz. So 20,000 divided by 240. So the n is given to be 20,000 beta 2 by beta 1. So 20,000 by 240 into the reciprocal of beta 1. So 120 by 50. So this is 2, 50, 200. So 2 zeros cancel. So beta 2 by beta 1, the multiplication factor will be 200. So the answer is C, 200. So 3, question 3, the answer is C. The answer is C. Okay. Now question 4. A super heterodyne receiver has been designed to receive radio stations in frequency band of 108 MHz to 157 MHz. Okay, so a super heterodyne receiver can receive radio station in the frequency radio stations in the frequency range of 108 MHz to 157 MHz. So the minimum required intermediate frequency, the image frequency, fall outside of the 108 to 157 MHz. So there is a carrier frequency, there is a local oscillator frequency, and then there is the image frequency. So the image frequency must fall outside the receiving range. So a super heterodyne receiver. So this so in this case, in the case of a super heterodyne receiver, in case of a super heterodyne receiver, the image frequency image frequency is known as FLO plus FIF. This is the image frequency. Now FC Now we know that we are transmitting a signal between 108 megahertz and 157 megahertz. So we know for a fact that FC is less than 108, is less than 157, and it is said that FLO is less than FC. So FLO is less than FC, and further this FLO plus FIF should be less than, should be greater than 157. So to FIF is greater than 157 minus FLO. Where FLO is less than FC and the FC is given to be, you can assume FC to be we can assume FC to be the average of these two, 108 plus 157 by 2. So if FC is this and FLO is less than this, so if FLO is less than this, so FIF has to be greater than 157 minus 108 plus 157 by 2. So this will be 157, FIF should be, implies FIF should be greater than 157 minus 108 by 2. So FIF should be greater than 157 minus 108 by 2. This can be further simplified as implies if FIF is greater than 157 minus 108 is 49. So greater than 49 by 2. Implies FIF is greater than 24.5. So the minimum required is 24.5 megahertz. So the minimum intermediate frequency required is 24.5 megahertz. Next, for 33% depth of modulation, the noise figure of an AM system is. So, depth of modulation for 33% depth of modulation, the noise figure of an AM system is. For 33% depth of modulation, the noise figure of an AM system. 33% depth of modulation means mu is equal to 33% or 0.33. So, mu is equal to 0.33. Therefore, mu square, this is the noise figure of AM, mu square by 2 plus mu square. So 0.33 square by, so here we have 0.33 square divided by 2 plus so 0.03, 0.05, sorry, 0.05, 0.05. So the correct answer is option D, 0.05. In the spectrum of a frequency modulated wave, the carrier frequency disappears when the modulation index is large. The carrier frequency cannot disappear. The amplitude of any sideband depends on the modulation index, and the total number of sidebands depends on the modulation index. Okay. In the spectrum of a carrier, see, the thing is, in frequency modulation, the modulation index is within the phase of the signal. So, what is the FM, SFM? It will be some AC cos omega ct plus omega ct plus this del k mt, where k is the modulation index. This is the modulation index. This is for phase modulation. Same applies for frequency modulation also. So let's rather do it for frequency modulation only to avoid confusion. Okay. So this is FM. Now the mode of the FM signal is always AC. So the phase of the carrier might change, but the carrier will never disappear. So option number A is wrong. And second, the amplitude and total number of sidebands does not depend on the modulation index. So here the modulation index is inside the phase. So it has no power to alter the amplitude. Thus, option B, question number 6, the option will be B. The carrier frequency cannot disappear. Okay, now let's go to 7. A diode detector load consists of 0.05 microfarad capacitor in parallel with a 8 kilo ohm resistor. The maximum depth of modulation without diagonal clipping at a modulating frequency of 60 Hz is. A diode detector load consists of 0.05 microfarad capacitor in parallel with 8 kilo ohm resistor. The maximum depth of modulation without diagonal clipping at modulating frequency of 60 Hz is. So question number 7. To avoid diagonal clipping, the optimum value of time constant is given as 1 by RC is greater than omega m mu by root 1 minus mu square. To avoid clipping, the time constant should be tau should be greater than omega m mu by root 1 minus mu square. So tau is 1 by RC. Sorry, 1 by tau, not 1 tau, 1 by tau. So 1 by RC should be greater than omega m mu. What is omega m? Omega m here is, and R and C all are given. So R and C are 0.05 microfarad and 8 kilo ohm. 0.05 microfarad. So 0.05 microfarad means is, so then let's put the values. 0.05 microfarad. So 5 into 10 to the power minus 8, and R is 8 kilo ohm. So 8 into 10 to the power 3 is greater than 2 pi. What is the frequency? The frequency is 60 hertz. 2 pi into 60 into, let's put this as m, where m is equal to mu by root 1 minus mu square. So here we will see that here the mu is, here we will substitute m as mu by root 1 minus mu square, and thus we will get 5 8s are 40, so 40 into 10 to the power 5 by 40 is greater than 120 pi m, implies m is less than 10 to the power 4 by 480 pi, implies mu by root 1 minus mu square is less than 10 to the power 3 by 48 pi. Implies, let's take square on both sides, mu square by 1 minus mu square is less than 10 to the power 6 by 48 square pi square, implies 48 square pi square mu square is less than 10 to the power 6 into 1 minus mu square. We can do this because we know that mu is less than 1. So mu square 10 to the power 6 plus 48 square pi square is less than 10 to the power 6, implies we will take only the positive root because we know mu is a positive number. So mu is less than 10 to the power 3 by root under 10 to the power 6 plus 48 square pi square. So if you do this in the calculator, 48 square into pi square, so we have 48 square into pi square, plus we will do 10 to the power 6. So we have this, and we will divide this thing 1022740 by 10 to the power 3. So 1022740. We will get 9.77 into 10 to the power minus 4. So this is the maximum modulation index you can achieve, 9.77 into 10 to the power minus 4. There's some kind of a problem in the calculation. Mu is this, mu. Okay, sorry. I forgot to square root this thing. 10 to the power 6, 10 to the power 6 plus 48 square pi square. 48 square into pi square So this thing, now this thing needs to get square rooted. Okay, 1011. So 1000 divided by 1011. 0.989. So mu is less than, not this thing, mu is less than 0.989. 0.989. So mu is less than 0.989, which is option A, no, 0.988. So the correct answer is option A. Now consider an AM signal given as phi AMT is equal to A plus XT cos omega CT, where A equal to 10 volt and XT is 5 into cos 2 pi 10 to the 3t and omega C is 1 megahertz. So the peak envelope power of the signal will be. So here we have a standard AM signal where there are some values of the amplitude, carrier amplitude, carrier frequency, and message amplitude and message frequency. So some typical values are given. Now so we will get A plus 5 into cos 2 pi into 10 to the power 3t. So the peak envelope power of the AM signal will be. Now the AM signal is given as phi t is equal to A plus xt cos omega ct. So the amplitude is this. So the peak envelope will be, peak envelope is achieved when A plus xt max. So PEP is mod equal to mod A plus xt max whole square. Now we know A mod A plus xt will only be maximum when, since A is a scalar, xt is maximum, and xt is maximum when this cos thing is 1. So 10 plus 5, 15. So the peak amplitude power will be 10 plus 5 into 1 whole square. So 15 square. So 225. So the peak envelope power will be 225 watt. It is D. Now let's go to question 9. If xt is having a power spectral density Sxx omega, the powers, if xt is having a power spectral density Sxx omega, okay, so the input power spectral density is Xx omega, the power spectral density of the output is. So we have two components in the output. One is the xt itself and another is a delayed version of xt. So yt is equal to xt minus xt minus t. This is yt. Now The power spectral density we will get by taking a Fourier transform. If we take a Fourier transform, YF is equal to XF, and when we do a time delay, we multiply by e to the power minus j omega. So e to the power minus j omega t x. So xf 1 minus e to the power minus j omega t xf. So this is, now if you do a PSD calculation, then mod yf square is the PSD of yf. So that will be mod 1 minus e to the power j minus j omega t whole square sxxf. So this will be mod 1 minus, this will be mod 1 minus cos omega t plus j sin omega t whole square sxxf is equal to 1 minus cos omega t plus sin square omega t sxxf. So this will be 1 plus cos square omega t plus 2 cos omega t. So 1 plus cos square omega t plus sin square omega t is another 1 minus 2 cos omega t sxxf. So finally we will have 2 1 minus cos omega t sxxf. 2 1 minus cos omega t sxxf. So option B. 9 is option B. An AM wave has a total transmitted power of 4 kilowatt when modulated 85%. How much total wave should a power should an SSB wave contain in order to have the same power content as that contained in two sidebands? So there is a total transmitted power of 4 kilowatt when modulated 85%, and that to have the same content as the, so we have a AM wave where 4 kilowatt is transmitted and 85% modulation is done. So how much total power should an SSB wave contain in order to have the same power content as that contained in two sidebands? So we have to find the total sideband power. So the question is to find the total sideband power. So the question is to find the total sideband power. This is what we need to find. Now, if you see a normal AM, it is A plus So here we have St equal to A plus Xt or A plus Mt into cos omega Ct. Now, if you expand this, you will get three components: AC cos omega Ct plus KAC cos omega C plus omega Mt plus KAC cos omega C. So the sideband power, total sideband power is K square AC square K square AC square by 2, and the total power is AC square plus K square AC square by 2. Now what is given is the total transmitted power is 4 kilowatt. So this total power AC square plus K square AC square by 2. This is 4 kilowatt. So 4 implies 4 kilowatt is equal to AC square into 1 plus K square by 2. And K square is given to be 0.85. So this is 0.85 square by 2 plus 1, 1.361. So 1.361 AC square. So AC square is simply 4 by 1.361. Therefore, total sideband power is AC square is 4 by 1.361. So it is 0.85 square by 2 into 4 by 1.361. So 4 into 0.85 square. 0.85 square square into 4. So 2.89 by 2 into 1.361. So 2.722. So 2.89 by 2.722. So 1.06. So 1.06 kilowatts. 1.06 kilowatt. So 1060 watt. So we have a correct answer at 1060 watt, which we can verify here. The answer is 1060 or 1.06 kilowatt. So the answer is option A. Next, assuming other parameters unchanged, if modulating frequency is halved in modulating system, then modulation index is doubled. If modulating frequency is halved, then modulation modulation index is doubled. So modulation index is not a frequency function in AM, but in phase modulation and frequency modulation, it is a function. So question 11 will be D. The answer will be D, both phase modulation and frequency modulation. In phase and frequency modulation, what we have is, say if we have SFMT, it is AC cos omega C plus KMT. So rather, let's KFM is, or KPM. KFM is proportional to delta F by F, and KPM is also proportional to delta F by F. But KAM is KAM is AM by AC, where AM is the message amplitude, AC is the carrier amplitude. So this does not depend on frequency. So it will be either phase modulation or frequency modulation. 11 will be A. Not A, sorry. 11 will be D. 11 is option D. 12. An angular modulated signal with carrier frequency omega c equal to 2 pi into 10 to the 6 is described by the equation, this thing. The carrier swing is given by. So, carrier swing is basically the variation of the carrier signal. The carrier swing is variation of the carrier frequency. So, the carrier swing is given as the variation of carrier frequency, and it is given as delta F. So, in this question, 10 cos omega ct plus 0.1 sine 2000 pi t. The 0.1 sine 2000 pi t. This is question 12. 0.1 sine 2000 pi t. So phi is this, omega ct plus 0.1 sine 2000 pi t. So the frequency f will be given as d phi by dt, which is omega c plus 0.1 into 2000 pi cos 2000 pi t. So this extra term, this is the delta f. This extra term is the delta f, the carrier swing. So what will be the maximum value? Maximum value will be when cos is 1. And when cos is 1, it is delta f max is this thing divided by 2 pi. Sorry, this thing divided by, whole divided by 2 pi. 1 by 2 pi. F will be 1 by 2 pi. So 200 pi by 2 pi. 0.1 into 2000 is 200. 200 pi by 2 pi. So 100. So this is 100 hertz. Delta F max is 100 hertz. Option A. 12 is option A. 100 hertz. So that concludes our problem solving session for analog communication. There are few more questions here which you can try at home. The solves the this webs this the PDF of this website will be provided to you, and this the recording of this video, so you can solve the remaining questions. If you have any doubt, you are free to communicate to us. And with that, I will like to conclude today's problem solving session, and further the problem solving session for analog communication concludes here. Thank you and have a nice day.